right? Uh, you all must be aware that materials usually, okay, I have to use the word usually because there are exceptions also. Materials usually expand when they are heated, means when their temperature increases. So temperature increases, the material expands. Okay. Can any of you think of some practical applications of this? Or if you have used this anywhere, you can share. Okay. Uh, you all must have used pressure cookers, no? Or you at least know why it is used and how it is used. Basically, what happens as temperature rises, okay, uh, pressure inside the pressure cooker increases. Okay, so when the contents of the pressure cooker reach a particular temperature, the gas in the pressure cooker also reaches that high temperature. Basically, what happens when gas temperature increases, it tends to expand. Not just gas, anything tends to expand usually. Okay. So when the gas expands, it pushes the vessel in the upward direction. It has to escape from the pressure cooker. So it pushes the vessel. That is also an example of thermal expansion itself. Gas is expanding or the steam inside is expanding. Okay. Uh, some other situations, Pawan said hot air balloon. Okay. That's a very good example actually. Basically, hot air means what? Air at higher temperature. When temperature of air is increased, it would expand. If a material expands, the same mass occupies a greater volume, means its density decreases. So hot air is less dense than cool air. Okay. So inside a balloon, if there is hot air, okay, I'll just use a circle to denote a balloon. Inside a balloon, if there is hot air, okay, hot air density is less, means molecules will be far from each other. Outside, there is cool air, means density is more. So basically, the situation is like an object of lesser density is immersed in a fluid of greater density. What happens when an object of lesser density is immersed in a fluid of greater density? The object tends to rise up or float. So inside there is hot air, outside there is cool air, cool or cold. Okay, I don't know which is the exact word to use. So hot air being less dense is like an object of lesser density in cool air, which is fluid of greater density. As a result, what will happen? There will be an upthrust on the hot air balloon. That is why the hot air balloon effectively rises. Okay. For it to come down, you will have to cool down the air inside. Only then the hot air balloon can come down. Okay. So they have to switch off the heat. Okay. Then only it can come down. Or they'll have to make the gas escape. Okay, that is impractical. Fine. So it is a well-known fact that materials expand when temperature rises. And usually that is what is found to happen. Now you can see this example on the left side. So basically it's a railway track. Okay. And due to some unexpected reason, the temperature might have risen to such a high value that the tracks expanded. Now they didn't have space to stretch. The track might not have had space to stretch, but its length has to increase. Then what will happen? Instead of remaining straight, the track will buckle like this. Okay. It will become curved, which obviously will lead to accidents if trains go on that. So what they need to do is they'll have to leave small gaps between rails. Okay, like the track is not a continuous metal. Okay, so they're like bars of metals placed next to each other. Okay, rails of metal placed next to each other. So between one rail and the next rail, they'll have to leave a small gap. In the image on the right hand side, basically you might have observed this on bridges, road bridges. Okay, so you can see that they have left small gaps here. Why is that? To accommodate for thermal expansion itself. When temperature rises, even a road bridge expands. Okay. So when the part of the bridge on the right side expands or the part of the bridge on the left side expands, they should have space to move. Okay. Small amount of space. That space is what they are providing here. There are many other applications of thermal expansion. Uh, you know that an iron box can switch off automatically when a certain temperature rises. Iron box or kettle, they can switch off automatically when a certain temperature is achieved. Okay, that switching off happens due to thermal expansion itself. Okay, they make use of thermal expansion to uh, enable the device to switch off itself. Okay. Now, basically, why does a material expand when temperature rises? Can any of you think of an explanation for this? Why should this happen? What has temperature got to do with size of the object? First, tell me this. Okay, if you understand this point, then you will be able to answer this. Suppose there are two objects. Okay, let's say there is a hot cup and a cold cup. It would have been better if I had shown an image, but that's fine. Imagine a hot cup of water and a cold cup of water. Obviously, if you touch the hot cup of water, you will feel hurt a little bit. Okay, it depends on the duration for which you touch. Why does the hot cup of water hurt while the cold cup does not? Now, don't say just because it is hot. Okay, I'm asking you, what does that mean for us? Hot means temperature is greater. That's okay. Why does it hurt more than the cold cup of water? That is my question. Can any of you think of an explanation? Why does it hurt when we touch hot objects? Okay. See, the answer lies in the meaning of temperature. Okay, I got one answer, one response as heat energy is transferred from the hot water. That is correct. Heat energy is transferred, but still, why does it hurt? Okay. So, temperature of the hotter cup is greater than temperature of the cooler cup. Now, basically, when something hits us, we get hurt, right? That is nature, basically. Now, temperature of the hotter cup of water is greater means molecules in the hotter cup of water are moving faster, okay, or they are vibrating faster. Fine. So there is more molecular vibration in a hotter object compared to a cooler object. There is more molecular vibration means what? When you touch that object, the hotter object, molecules are vibrating very fast. So it's like they hit you harder than when you touch a cooler object. Okay. So when you touch a hot object and a cool object, the molecules of the hotter object hit you harder. That is why you feel more hurt than a cold cup or the cooler object. So remember, temperature is a measure of molecular vibrations. Okay, that is what is temperature. In case of gases, you can say it's a measure of the random movement of molecule altogether. Whereas in solids and liquids, molecules are not that free to move. Okay, they stay at one place, but they keep vibrating about that place. Okay, they are not at rest. In solids also, the molecule is not never at rest, except at 0 Kelvin, absolute zero of temperature. At any non-zero on the temperature on the Kelvin scale, in solids also molecules will be vibrating. Liquids also molecules will be vibrating. In fact, in a liquid, it is possible for molecule to move around also a little bit. In gases, they are completely free to move around. Okay, so temperature is a measure of molecular vibrations or molecular motion. You can say that also. So higher temperature means more molecular motion. Okay. Now you consider an object. Let's say a solid object. There will be some, I mean, even in solids, there is gap between molecules. Okay, we know that in solids, molecules are tightly packed. That doesn't mean there is no space between them at all. Okay, there will definitely be space between them. Now, you all must have learnt about something called bond length. Okay, especially those of you who have studied 11th class, you must have studied bond length. What is bond length? Bond length is basically the average distance between two atoms in the bond. Okay, atoms form bonds, right? So this average distance is what you call as bond length. Carbon-carbon bond length and all you must be studying. Now, even atoms in a bond, in a molecule, they are not at the same distance always. This atom will be vibrating. This atom also will be vibrating. They'll be coming closer and going farther. Okay, so average distance is what you call as bond length. So between atoms itself, there is space. Then between molecules, there will definitely be space. Okay, so consider a solid like this. Let's say let's say these are the molecules. There will definitely be space between them, and molecules are never at rest. Okay, they'll be vibrating, and they'll be vibrating randomly in all directions. Okay, there's no fixed direction in which a molecule should vibrate. Okay, now as the molecules vibrate, they need space around them. They have that space also. Now, one of you tell me what happens or what should happen if the molecule wants to vibrate to a larger distance. What should happen to the object as a whole if molecules need more space to vibrate? Will it contract, expand, or nothing happens? If molecule needs more space to vibrate, what should happen to the object or the material as a whole? Obviously, it will have to expand. Okay, this is the exact reason for thermal expansion. When temperature rises, molecular vibration, okay, in the solid increases. Molecular vibration increases means what? The distance up to which they oscillate increases. The distance up to which they oscillate is called amplitude. You will learn this term in more detail in the next chapter, oscillations. Okay, next concept. But basically, the distance up to which a molecule moves away from its mean position is what you call as amplitude. So amplitude of molecular vibration increases. So molecules will need more space, obviously, between themselves. So what happens is all the molecules start moving away from each other. Now the molecule size does not change, but the space around the molecule changes. So they will all need more space like this. This is what is basically thermal expansion. So at lower temperature, the material may look like this. At higher temperature, it looks like this. Okay, and it exactly happens like this. Expansion happens in all directions, not in one particular direction. In fact, on the screen, it may look like expansion happens in two dimensions, x-axis, y-axis. Okay, but in 3D, if you think about it, three-dimensional object, expansion happens in the z direction as well. So basically, the object or the material bulges. In all directions, it will expand. Now, the opposite happens when you decrease temperature. If you decrease temperature, amplitude of molecular vibrations decreases. So molecules will need less space, less free space between them. But see, molecule-molecule attraction will be there anyway. That is how a material stays together. No, like you take any solid object, for example, consider this. Okay, this wedge that I'm holding. There is intermolecular attraction. That is how they are all able to stay together. Fine. If you raise its temperature, molecules will still be attracting each other, but they need more space between them. Okay, so the object will expand, but it will stay as a one object. Okay, provided you are not raising it to such high temperatures that it reaches melting point. Similarly, if you cool it down, molecular attraction will be there, and now they don't need much space between them when you cool it down. So what will happen? It will shrink. So that is the basis of thermal expansion, and we will restrict our discussion to expansion of solids and liquids. Expansion of gases will be dealt with separately in the next part of this chapter called thermodynamics. Okay, fine. So remember, thermal expansion. See, what did I do here? I copy pasted the image. Okay, image or the diagram. I copy pasted the diagram and then just enlarged the diagram. Okay, I zoomed in. Thermal expansion is exactly like that. Thermal expansion is like photographic zoom. So if you want to imagine an object which undergoes thermal expansion, just imagine it being zoomed in. If you want to imagine an object which undergoes thermal contraction, imagine zooming out. That's all. Okay, that will help you visualize thermal expansion and thermal contraction. Okay. Now, as I said, expansion, when you raise temperature, expansion happens in all directions. But in some objects, the expansion in one direction will be much more significant than expansion in other directions. Okay. Now see, basically, uh, how much a material expands depends on these factors. Now you consider a set of molecules like this. Okay. Take 5 molecules, for instance, and consider another set of, let's say, 10 molecules. Let's consider a solid object. Let's say this is one object made of 5 molecules. Okay. Actually, an object made of 5 molecules, you won't be able to see it also. So this is just a hypothetical example. Consider another object made of 10 molecules. So what is different between them is their size. They are made of the same material, let's suppose. Now, at one temperature, let's say temperature T1, let this be the situation. Okay. Assume at temperature T1, the gap between the molecules is x1. They need that much space between themselves. In both the objects, it will be the same, x1 and x1, because they are made of the same material. Now you raise the temperature. If you raise temperature, both objects will expand. Okay. So the molecules will need more space between them. Let's say the space between each pair of molecules now is x1 plus some extra space. Let us denote the extra space by delta x. Okay, that is the space needed between the molecules. Now the same will happen with the other set as well. This other set also would have expanded. Okay, I'll show it here. And the space between molecules of the other set. Stop. Okay, just a moment. Right, it's somewhat like this. Fine, fine. So the space between molecules of the other set also, any pair of molecules of the other set also now is x1 plus delta x. Some extra space. But this delta x, okay, x1 plus delta x is between two molecules. Fine. Now see, totally how many gaps were there in the first object? 4 gaps were there. So its original length was 4x1. Okay. Here I think there will be 9 gaps. So original length here is 9x1. What is the final length of the first object? 4 times of x1 plus delta x. So that is 4x1 original length plus 4 delta x expansion. That is how much it has expanded. What is the final length of the second object? There are 9 gaps. So 9 times of x1 plus delta x. So that becomes 9x1, which is its original length, plus 9 times of delta x. This is the expansion. Okay. Now observe one thing here. The expansion of the object, they're both made of the same material, that's okay. But still, how much they expand for a certain rise in temperature depends on the original length. When the original length is 4x1, the expansion is 4 delta x. When the original length is 9x1, the expansion is 9 delta x. So more the original length, more the expansion. Fine. Therefore, Thermal expansion means how much an object expands when you raise its temperature depends on its original dimensions. So expansion means thermal expansion here, depends on original, or okay, let's not call it original also, initial dimensions. Of course, another factor on which expansion depends is the temperature rise. If you raise the temperature only a little bit, only a little bit of expansion will happen. If you raise the temperature more expansion will happen. Obviously, it should depend on that. And another factor on which it depends is the material as well. Now see, molecules of all materials don't have the same attraction between them. In some materials, molecules attract each other very strongly. In some materials, they don't attract each other that strongly. So where the molecular attraction is very strong, it is difficult to expand that material. But if the molecular attraction is weak, that material can expand very easily. Okay, so it depends on material as well. So these are the factors on which thermal expansion depends. Okay, now when you raise temperature, as I said, material expands in all directions. Length will increase, height will increase, thickness will also increase. Fine. Now if you want to consider the change in length, you call that as linear expansion. Okay, so basically this example itself, you see the one you see on your screen, the length increases along the x direction and the length increases along the y direction as well. You can call it height if you want. Basically, it's a length only. So length in this direction can increase, in this direction can increase. You can take some other direction also. In that direction also, the length will increase if you raise temperature. You can also say that when looking from this side, it appears as if the area is increasing. Okay, so this is the initial area. This is the final area. So you can say the area is increasing. Obviously, when length and height both increase, the area increases. You can also say volume is increasing, right? So we define three different kinds of thermal expansion. Basically, it's just what you want to measure. It's just related to what you want to measure. You want to estimate the final length, then you call it linear expansion. You want to estimate final area, you call it areal expansion. Okay. You want to estimate volume, you call it volume expansion. Actually, all three will happen. Length, area, volume will all change. Which one you want to calculate, based on that, you will have to use a different formula. That's all. Now, expansion depends on initial dimensions, the rise in temperature, and the material. Okay. So based on all these factors, we can write formulas like this. Suppose you want linear expansion. You want to find out how much the length will increase. Okay. I'm telling you again, linear expansion is increase in length doesn't mean increase in one dimension. You can take length in any direction. Okay, there's no restriction to the direction. Suppose there is a cube that you are heating or a cuboid that you are heating. Change in length is linear expansion. Change in breadth is linear expansion. Change in height is also linear expansion only. So change in any kind of length is called as linear expansion. Okay, for example, let's say there is a ring you are heating, then change in radius is linear expansion. Change in diameter is linear expansion. Change in perimeter is linear expansion. Fine. So you express it like this, delta L. Okay, expansion in length. Okay, that length could be of any kind, is equal to, or it depends on initial length and it depends on temperature change and the material. Okay, temperature change is denoted by delta T. Usually we denote change with delta T. No? So combining all these factors, we can say that change in length of the object is equal to original length into temperature change multiplied with a value called alpha, which is basically coefficient of linear expansion. And that value depends on the material. Okay, you can also call it thermal coefficient of linear expansion. Okay, that factor depends on the material. So this is the formula for linear expansion. Delta L is equal to initial length L naught alpha delta T. What does delta L mean? Change in length. So you can write change in length as final length minus initial length is equal to L naught alpha delta T. Therefore, The final length can also be expressed as initial length plus L naught alpha delta t, which is L naught into 1 plus alpha delta t. So you can use any of these formulas to find out the final length. So this is the formula for linear expansion. There is another variation of this formula also, which we'll discuss in the next class. But I just wanted to show you that this formula is derived based on the fact that expansion depends on initial dimensions. So linear expansion depends on initial length. It depends on temperature rise. Obviously, greater the temperature rise, greater the expansion, and it depends on material. That material factor is given, how we include that is by means of alpha. Okay, they will have to give you alpha in the question. Okay, if it's a steel object that they're asking about, they'll have to give you alpha value of steel so that you can substitute and find out the final length. Or they can give you these expansion, original length, and temperature change and ask you how much is the alpha of steel. Such questions can be asked. Any one of these can be asked. Okay. Another kind of expansion is areal expansion. I should not actually say another kind of expansion. Another thing which expands, another quantity which expands is area. Okay. So if you want to find out how much the area is expanding, then change in area, obviously, as I said, it is proportional to initial dimensions. No. So it is proportional to initial area. It's proportional to change in temperature and it depends on the material. Put all this together. You get change in area is equal to initial area, temperature change, and the material factor. Material factor this time is called coefficient of areal expansion. Or thermal coefficient of areal expansion. That also varies from material to material. They'll have to give you that in the question. And you can even write the formula like this. Final area is initial area into 1 plus beta delta t. Okay. You have one formula for length, one formula for area. Similarly, there is also something called volume expansion. You can, or you might want to find out how much the volume has expanded. Okay. In that case, expansion in volume proportional to original volume, proportional to temperature change. Put all these together. Expansion in volume will be original volume multiplied with temperature change multiplied with a factor which depends on the material. We denote it by the symbol gamma. This is called coefficient of volume expansion or thermal coefficient of volume expansion. So you can write final volume is initial volume into 1 plus gamma delta T. Okay. So this is the fundamental concept behind thermal expansion. Molecules need more space and they need more space in all directions, not just in one particular direction. So expansion happens in all directions. So if you want to measure linear expansion, you use one kind of formula, like calculate. If you want to calculate expansion in area, you use second formula. If you want to calculate expansion in volume, you use the third formula. And if volume expands, okay, see for a given mass, if volume increases, density decreases. So when volume expands, there is density decrease happening. Okay, you can relate them. And see, linear expansion, areal expansion, volume expansion, these three also can be related. How much the area increases depends on how much length and breadth increase. Okay, like you consider this picture itself, this diagram itself, the area is increasing. We know that. Okay, like in the first case, this is the area that you see. In the second case, this is the area that you see. But how much the area increases depends on how much the length and breadth increase. Okay, so areal expansion depends on two linear expansions. And volume expansion depends on three linear expansions, x direction, y direction, and z direction. Okay, so you can relate their coefficients. Coefficient of linear expansion, that is alpha, okay, can be related to coefficient of areal expansion beta, and also can be related to coefficient of volume expansion gamma. Okay, so the relation between these three and how to make use of all these formulas in problems, okay, and how to find out change in density based on change in volume, all these things will be the topic for tomorrow's class. Okay, that is what we are going to discuss tomorrow. And there is something I would like you to revise and come. Okay, those of you who have already studied 11th, you must be knowing this already. There's something called binomial expansion, okay, and binomial approximation. We had discussed this in the initial classes. And I think we used this also very recently. Anyway, 1 plus x whole power n, what is it approximately equal to? Okay, if x is very small compared to 1, what is 1 plus x whole power n approximately equal to? Revise that. And anything else you need to revise? That's the first thing. Next thing is integral 1 by x dx. Okay, just revise these two formulas. Some of you might not be knowing integration. Okay, I hope you all know integration. If you don't know, that's fine. Revise these formulas, they'll be useful in the next class. Okay, thank you all. We'll continue tomorrow. And try to join on time. Some of you are joining late, but basically, if we start late, we'll have to close the class later. Some of you will be having school, college, and all, no? So I want to close the class at 7:15. So try to join on time. Okay, thank you all.